Somewhere in a galaxy not unlike our own, an ordinary star is about to have a very bad day. It's drifted too close to something with a gravitational pull so extreme, physics has an actual, literal term for what's about to happen to it: spaghettification. And here's the part that took astronomers years and one incredibly lucky observation to actually confirm. They had two competing theories for what happens next, and for a long time, they genuinely couldn't tell which one was right. At the center of most galaxies sits a supermassive black hole, millions, sometimes billions of times the mass of our sun. Gravity gets weaker with distance, so as a star drifts close enough, the black hole pulls noticeably harder on the near side of the star than it does on the far side. Cross a specific boundary called the tidal radius, and that difference in pull becomes stronger than the star's own gravity holding itself together. The star stretches into a long, thin stream, spaghettification in the literal sense scientists use the word. Roughly half of that stellar material gets flung outward into space. The other half stays gravitationally bound and starts falling back in. That returning material doesn't just fall straight in, it swirls into a hot, rotating accretion disk around the black hole. Friction inside that disk heats the material to extreme temperatures, producing a bright flare of ultraviolet and X-ray light, bright enough to be seen across truly enormous cosmic distances. Here's the part that stayed genuinely unresolved for years. Astronomers had two competing explanations for exactly where that flare's brightness actually came from. One theory said it was the heated accretion disk itself. The other said it came from the spaghettified debris streams slamming into each other. In 2020, astronomers led by Matt Nickel caught a huge break, the closest tidal disruption event ever recorded, just 215 million light-years away, and they caught it early, before it reached full brightness. Watching it unfold in real time, they measured rapid outflows of material lining up with the disk accretion explanation. It was the strongest evidence yet for one side of the debate, though even that team was careful not to call the question fully, permanently closed. Here's a detail almost nobody expects. Not every black hole can actually produce one of these events, even a very large one. Only black holes below roughly 100 million times the sun's mass can actually tear a sun-like star apart outside their event horizon. Go bigger than that, and the event horizon itself is so large, the star gets swallowed completely intact. No stretching, no flare, nothing for astronomers to ever see. Which means some of the most massive black holes in the universe are eating stars in complete silence in a way we have essentially no way of directly observed. On the scale of one single galaxy, this is a genuinely rare event. Astronomers estimate any individual galaxy only produces a tidal disruption event roughly once every 10,000 to 100,000 years. But zoom out to the entire observable universe with its uncountable galaxies, and astronomers now catch several of these flares every single year. And upcoming telescopes, like the Nancy Grace Roman Space Telescope, are expected to push that number up to around 100 a year, turning what used to be a once-in-a-career discovery into something closer to a routine catch. So, what really happens when a black hole eats a star? Physics tears it apart along a precise, measurable boundary. Half its mass escapes forever. The other half swirls into a blaze of light bright enough to cross hundreds of millions of light-years. A light astronomers only recently confirmed the actual source of, and only for the black holes small enough to let us see it happen at all. Somewhere out there, right now, this is probably happening. We just haven't pointed a telescope at it yet. That's your OHpedia for today. If this made you go, huh, I never knew that, share it with someone whose brain you like.